Let's start this lesson by just having a quick review of Boolean algebra, especially the simplification side of things. Often I find that students over time might need a lot more practice to simplify, especially the distribution and the absorption laws. And hopefully these two examples that we're going to go through will help you understand how to simplify Boolean expressions. So let's start with the first one, A or B and A or C. Now the first step is to open the brackets up so we can simplify the terms. So in this particular case, we can just simply do A and A, or A and C, or B and A, or B and C. If you know your identities and laws really well, you can just simplify everything in one step. But what we're going to do is to do it step by step so you can actually understand how the process actually works. Now, if you look at the first term, A and A, the Boolean identity in the first block equates to an A. And if you really wanted to kind of look at it, if we give A the value of 1, 1 and 1, you pass two ones through AND gate, you get the output as 1, which is essentially A. So A and A will give us an A because 1 and 1 gives you a 1. So the expression now becomes A or A and C, or B and A, or B and C. So now we're going to look at the next set of expressions. So if you look at A or A and C, look at the absorption laws. That's the same as the first absorption law, X or X and Y, which equates to X. Now you can substitute X for A and Y for C, and that means that that resolves to X. And since X is A, the answer to A or A and C is A. Now you could also try this using actual values, like if A is given the value 1 and C is given the value 1, so you have 1 or 1 and 1. So let's look at 1 and 1. 1 and 1 will give us the output of 1, and 1 over 1 will also give us an output of 1. So that whole expression will eventually resolve to 1, which in this case is A. And you can do the same thing again, A or B and A, that can resolve to A using the same absorption law. In the end, you're left with A or B and C, and that cannot be simplified any further. And that's where we stop, because each of the terms are different. Now let's look at the second example, A or B and A or A. Now straight away, looking at the Boolean identities, A or A equates to A because 1 or 1 will give you a 1. So that's pretty straightforward. The second bracket solves itself. Now we can rearrange the expression to make it easier for us to understand by shifting A to the left-hand side. A and A or B is the same as A or B and A. You can work out which law, probably the associative laws, are useful here. Now if you're looking at A and A or B, you can see the Boolean expression in the absorption law. Once again, it's pretty common, and that all resolves to A. So this is a pretty straightforward simplification. Everything resolves to A. Now hopefully that gave you a bit more clarity on how to go about resolving Boolean expressions and how to simplify them. We're going to move on with the purpose of today's lesson, which is to look at producing truth tables for logic circuits, including some special circuits which are known as half adders and full adders. We're then going to move on to flip-flops, which are useful in creating memory structures. So we're going to be looking at two in particular, the set reset, SR, and the JK flip-flops. Now to move on with today's lesson, you need to have a good understanding of logic circuits and the base logic gates and their truth tables. And if you're not sure about those, then my suggestion would be to watch the year 12 video where we talk about logic circuits and logic gates, and make sure that you're familiar with all of those before continuing. And as usual, we're going to start with looking at some key terms. So do pause the video and make sure you jot these down. You should be aware of what a half adder circuit is. Now you know that logic circuits can be created for multiple purposes. A half adder circuit allows us to carry a binary addition because the purpose of computers is to add and work with numbers. Then we're looking at the full adder circuit, which is basically two half adders combined, and that allows us to add a lot of different binary digits. So the half adder circuit has a limitation which the full adder corrects. You also need to know the difference between combination circuits and sequential circuits. Combination circuits are what we've been experimenting so far. These circuits, the output entirely depends on the input values, and sequential is something we're going to be looking at where the input depends on the output of the circuit itself, so we can in effect create a loop. And of course there are flip-flop circuits, cross-coupling, and the concept of positive feedback, which is to do with output influencing the input. So pause the video and go through these key terms and make sure you jot these down. Now let's start with the half adder circuit. One of the most basic operations in any computer is binary addition. So think about this. 1 plus 1 gives us 2, and in binary 2 is 1, 0. So how do we get a computer to use two inputs A and B and give us two outputs? A logic gate only gives us one output. In this case, we will need to create a logic circuit, and the most basic circuit, or the simplest circuit you can create, is the half adder circuit, which can do addition. It simply adds two bits together and gives you the output. Now it has two outputs. One is called the sum bit and the other one is called the carry bit. So if you're adding 1 plus 1, we'll get 0 on the sum part and 1 on the carry part. Now this type of circuit uses two logic gates. The first one is an exclusive OR and the second one is an AND gate. Now you can see the diagram on screen, and if you wanted to, you could probably create the truth table for the entire circuit yourself, and you will need to do that for the exam. So do pause the video and have a look at the circuit diagram carefully. Make sure that you know how to create a half adder circuit and how to work out the truth table for the half adder circuit. Now sometimes the circuit diagram will be given to you as that square symbol which says a 1-bit half adder. That's fine as well. Sometimes you'll be asked to draw the circuit diagram, so make sure you know how to do that. And sometimes you'll be asked to work out the truth table for it, so you should be able to do both of those things. Now an extension task for you is to try to create the same output using a different combination of logic gates. And there are multiple ways to do that, because if you think about industry, we don't want to have too many gates. We want to kind of have the same gate, because then we can leverage economies of scale and reduce costs. Try to create your own combination that gives you the same output, or if you want an even bigger challenge, try to create the same output using just one type of gate. That's going to be a significant challenge. Now let's move on to the full adder circuit. The half adder itself can do addition, but it's unable to deal with the addition of several binary bits. For example, perhaps you want to add an 8-bit byte or two 8-bit bytes together. Now to enable this, we have to consider the full adder circuit. So on screen you can see a truth table that deals with this and how it can cope with multiple bits together. So A and B are your inputs, sum and carry are what they are, and you can see what's going on. So 0 plus 1, so let's start with the right hand side. 0 and 1 gives you a 1. This is the sum, which works really well. The next set of bits are 1 and 1, which will give you a 0, and a 1 goes into the carry column. Then you get 1 and 0. Now you've got two 1s, so when you add two 1s together, you end up with 0 for the sum and another carry. And finally you add 0 and 0. Obviously the answer will be 0, but if you add the carry bit at the bottom, the sum is 1. And that allows you to add, in this case, 5 bits together and still get to the correct answer. So the correct answer for this is 1 0 0 0 1. That would be the answer for adding 0 1 1 1 0 and 0 0 0 1 1. Now you can work it out yourself and you should arrive to the same answer. Now creating the full adder circuit isn't that different from a half adder, because a full adder just basically is two half adders combined with an OR gate. On screen you can see the block diagram for it. Now I would like you to perhaps pause the video and maybe create the actual logic circuit diagram. Now you could use the two gates that I've used to create a half adder, or you could perhaps use the one that you came up with. Whichever method you want to do, try to actually get a complete circuit. Using my particular circuit diagram for the half adders, you probably should have 5 gates. You should have 2 inputs A and B, which go into the first half adder, and then you've got the carry in, which goes into the second half adder. The second half adder will take the input from the half adder, so that's the sum bit from the half adder, that goes into the second half adder, and then obviously the carry in goes into that one as well. The carry out from the first half adder goes into the OR gate, and the carry out from the second half adder, that also goes into the OR gate, and both of these can combine into the carry out for the entire full adder circuit. The sum output from the second half adder becomes the sum output for the entire circuit. So try to create this circuit diagram, and then you can compare it to the one I have in the next screen in a moment. Your outputs will be exactly like the ones that you see in the table in the top right hand corner. You might want to use that as a test bed. And the sum basically shows how we've got to deal with the carry from the previous column, and this mechanism could be looped, and we'll get to that when we talk about flip-flops, and that could become the input as well. So it gives you some kind of positive feedback. Now here there are obviously 3 inputs to consider in this third column. For example, A in this case is 1, B is 0, and C is 1, which gives you the sum of 0. So if you just look at that particular column, which is outlined in red on the top right hand corner, that's what I'm talking about. And this is the reason why we need to join the 2 half adders together to form the full adder, because we want to take into account the carry from the previous operation and add it to the 2 inputs. And the second half adder does that. So hopefully you got something like this. And as with the half adder circuits, different logic gates can be used to produce the full adder circuit as well. However, for the exam purposes, you might just want to stick with this particular type of diagram because it's pretty easy to recreate in an exam, and the relevant truth table is on the right hand side. And you should be able to create this from memory as well. So do pause the video and understand these. If you didn't manage to create your own full adder, this will be very useful to you. So pause the video, go through this, and then continue. Now this is the right time for you to just do a task away from the screen. Hopefully you created your own half adder and perhaps a full adder. But what I want you to do is try to see if you can create this using just NAND gates. Now if you took part in the initial challenge, you might have already gotten to this particular stage. But try to create it using just NAND gates only and work out the truth table for your design to check whether you get the right answers. In industry, NAND gates are generally preferred compared to NOR gates to build circuits. What I want you to investigate is why that's the case. Why are NAND gates preferable than NOR gates? Is it cost? Is it efficiency? Whatever the reasons, I want you to find that out. Okay, so pause the video and have a go at this particular task. Okay, we're going to now move on to the types of logic circuits. So far, all of the logic circuits that you probably have encountered are combination circuits. That basically means that the output depends entirely on the input values. So A and B give you X. And now we're going to move on to a second type of logic circuit, which is known as a sequential circuit, where the output depends on the input value produced from a previous output value. So you could link the output to the input, and that ensures that the new output is slightly different than the previous one. And examples of sequential circuits include flip-flop circuits, and you need to know 2 types of flip-flop circuits, and they are the SR flip-flops and the JK flip-flops. We're going to be looking at these 2 particular ones because they are the ones you need to focus on in the syllabus. We're going to start by looking at the SR flip-flop, and the SR flip-flop basically is the set reset flip-flop. S stands for set, R stands for reset, and these flip-flops consist of 2 cross-coupled gates, and you can make them out of NAND gates or you can produce them from NOR gates as well. The image that you see on screen is a circuit that's created out of NOR gates. So what happens? Why is it called cross-coupled? Well, that's because the output feeds into the input of the other NOR gate. So if you look at gate X, the output Q becomes the input for gate Y. Similarly, the output from gate Y becomes the input for gate X. And the other 2 inputs for the respective gates are the set or the reset, which basically is A or B in plain terms. Now the concept of cross-coupling or positive feedback is introduced here because the output from each NOR gate gives a form of positive feedback as it influences the output for the next cycle. Let's now look at the truth table which matches this SR flip-flop circuit. And we're going to start by using the initial states R equals 0, S equals 1, and Q equals 1. Why not any other combination? You probably could do that, but the sequence is going to be in this particular order because it starts somewhere. So let's start with this one. What happens as a result of this? That when Q is 1 and when S is 1, you get 1 and 1 into the second NOR gate. And the result of that, the output, not Q, is 0. And now that becomes the input for the first NOR gate. So now you've got R equals 0, not Q as 0. And when you pass that to a NOR gate, you end up with 1. So you can see how the cycle will just continue like this forever. Now what that basically means is we are now going to store that bit 1, Q is equal to 1, forever in this circuit, because it's just going to keep on going on forever. Provided there is electricity, it will retain that bit, so it acts like memory. So consider what happens if we now change the value of S from 1 to 0. So both R is 0 and S is 0. So now Q is 1 and S is 0. So 1 and 0 in a NOR gate gives you 0 again. That 0 goes back into the first NOR gate, 0 and 0 gives you 1, and then we're looping again. So in effect, we end up with the same pattern. Now that's fantastic because that bit is still being stored and the input doesn't make a difference here. Now what I would like you to do is to go through all the other possibilities to verify the truth table. And hopefully you will get something like the table on the right hand side of your screen. And you will probably notice a pattern that Q and not Q change depending on the combination or certain combinations of inputs. So pause the video and check this. Okay, so hopefully you verified that everything is how it's supposed to be. Now let's just decipher what's going on here. Now if you look at the very first example, A, S is 1, R is 0, Q is 1, and not Q is 0, this is called the set state. Now if we change the set state S to 0, that's known as the reset state. Now both of these give you the same output. In C, we change reset to 1, so the R goes to 1, and that has an impact on the output. Not Q becomes 1 and Q becomes 0. Now the truth table shows how an input value of S equals 0 and R equals 0 poses no change to the two output values. However, S equal to 0 and R equals to 1 reverses the two output values. S equals 1 and R equals 0 always give Q equals 1 and not Q equals 0, which is basically the set value. So depending on the combination, we can reverse the output. For example, if we wanted to store something, we set it, and when we want to clear it, we reset it. Now this means that the SR flip-flop can be used as a storage or a memory device for one bit. And because a value can be remembered, but it can also be changed, this particular flip-flop can be used as a component in a memory device such as a RAM chip. The only problem with this though is the last set of inputs, S equals 1, R equals 1, and that's where the problem lies, because you end up with both Q and not Q equal to 0. It's important that this particular fault condition is considered when designing and developing storage or memory devices, because there can be instances where you end up with ones at both set and reset, and that could mean that the bit that you are trying to store is actually lost, and that could have significant consequences when we're operating with program memory and eventually applications such as financial data and all sorts of things. Now, you might not send two ones for S and R. However, the inputs might not arrive at the same time due to some kind of disruption down the path, and the flip-flop as a result can become unstable. For example, let's just say you already have a 1 at reset and you've got a 0 at set, but the next set of inputs you're sending are 0 for reset and 1 for set. And for some reason, that 0 gets delayed and the 1 arrives. Now the reset is already 1 and the set is 1, and that could lead to instability as well. So what's the solution to this? Well, the solution was invented by an engineer called Jack Kilby, and his name now goes with the flip-flop called the JK flip-flop. So to overcome the problems of the SR flip-flop, a couple of additional elements were added to its design. A clock and some additional gates, which end up helping to synchronize the two inputs and also prevent those illegal states where you end up with 1 and 1 for the inputs and 0 and 0 for the output. The addition of the synchronized input gives 4 possible input conditions to the JK flip-flop, because you've got your S and R, and then you've got your clock, and then you've got a toggle which takes care of that invalid S or R state. Now, you need to pause the video and you need to study the JK flip-flop circuit. You should be able to recreate this. The one that you see on screen is made of NAND gates because that's perhaps the most simplest one to remember. So pause the video and understand the circuit diagram. Now on screen you will also see the circuit diagram with a simplified truth table for the JK flip-flop. Try to use the J and K values. So J basically set, K stands for clear or reset. Try to put these values in and recreate this truth table so it makes more sense to you. Okay, so start with the first one where both of them are 0. Now do remember that the first 2 NAND gates are 3 input NAND gates. So you've got J, you've got NOT Q, and you've got a clock pulse there as well. And the purpose of the clock pulse is to ensure that if you eventually end up with a condition where both J and K are 1s, the clock pulse is the deciding factor, and that ensures that the outputs don't become 0. And if you wanted to kind of do the 3 input NAND gates, you can work out a truth table for that. But eventually you're going to arrive to something like what you see on screen. So do pause the video and take your time. It'll probably take you about 5 to 10 minutes to kind of go through this properly and make the various truth tables for the 3 input NAND gate and the output then feeding into the next NAND gate and then eventually feeding onto Q, and vice versa for NOT Q. But hopefully you'll arrive to the same results as what you see on screen. So JK flip-flops solve that particular problem by using a third input of a clock pulse, which acts as a toggle. Okay? And the whole point of that toggle is to ensure that we don't have that state of 2 1s going into the circuit and producing an unstable output. So why do we use JK flip-flops? Well, we use them to produce shift registers in a computer. So remember binary shifts from AS, that can happen using JK flip-flops. And we can also create simple binary counters by linking up several JK flip-flop circuits together, because that requires a toggle function which is available in a JK flip-flop. Now you can do some additional research here as well, and you can find out how JK flip-flops can be used for both shift registers and binary counters, how computer architecture can be created using flip-flops. But for the exam, all you need to know is the uses of JK flip-flops, and those 2 on screen are sufficient enough. Now to summarize this entire section on flip-flops, the SR flip-flop, or latch as is sometimes called, is a simple example of a sequential circuit. It can be constructed with 2 NAND gates or 2 NOR gates, and they feed into each other. The flip-flop is a 2-state device. Either it has Q set to 1 or not Q set to 0, or it has the reverse of that. The 2 lines of the truth table where both S and R are input as 0 produce no change in the values set for Q or not Q. This is the condition when no signal is input to the flip-flop. Input of S equals 1 and R equals 0, always produces Q equals 1 and not Q equals 0. Input of S equals 0 and R equals 1 always produces the reverse of that. So not Q becomes 1, Q becomes 0. Now this explains why the SR flip-flop can be used as a storage device for just 1 bit, and therefore it could be used as a component in RAM because a value is stored but can also be altered. The circuit must be protected from receiving input on R and S simultaneously, because this leads to the invalid state where both Q and not Q can be set to 0. And to avoid that, we can use the JK flip-flop. In addition to the possibility of entering that invalid state, there is also the potential for a circuit to arrive in an uncertain state if inputs do not arrive at the same time. So they have synchronization issues. And in order to prevent that, the JK flip-flop introduces an element which is called the clock, and it also has 2 additional gates. Now the workings of the circuit can be viewed in terms of the value of Q output immediately after the circuit detects a clock pulse, and the J input acts as a set input, the K acts as the clear or the reset, so there is some similarity to the functioning of the SR flip-flop. However, if both J and K are input as 1, then Q always switches value, and that happens because of the clock pulse. Now as long as you remember that, you're going to be pretty much okay in the exam. And that's where we're going to end the lesson for today. Hopefully you should be clear about the purpose of the half adder and the full adder circuits. You should be able to construct half and full adders. You should be able to also construct a JK and SR flip-flop circuit diagram. And you should be able to explain the issue with SR flip-flops and how it can be resolved using a JK flip-flop. That's all for today. If you do have any questions, as usual, please get back to me, and I will see you in the next lesson.